Hello and welcome to the Prairie Ridge AP Physics Homework Solutions. We are going to be concentrating on difficult fluids book problems today. So we're in chapter 15 and I'd first like to look at problem 25. In problem 25, you have a patient in a hospital trying to receive an intravenous injection of medicine. And in order to work properly, the pressure of the fluid containing the medicine must be 109 kilo, which is times 10 to the third for prefix pascals, at the injection point. So part A asks if the density of the fluid is 1,020 kilograms per meter cubed. Find the height at which the bag of the fluid must be suspended above the patient for that to work. So we don't know what H is. For this problem, I used the pressure at depth equation. P equals P naught plus rho GH. So if I needed the pressure to be 109 times 10 to the third pascals, and I know that atmospheric pressure is 1.01 times 10 to the fifth pascals, plus my density, 1,020 times gravity, which is 9.8 times H. And from that, I found the height to be 0.8 meters. And part B goes on to ask that if you were a less dense fluid, so if the density decreases, would the new bag need to be suspended higher or lower? And it turns out if the density is decreased based on our equation, then the height would have to be increased to give the same amount of pressure. The next question I would like to look at is problem 28. And in 28, they're talking about having a pair of walking on water shoes. Wouldn't that be nice? Where one side is 0.25 meters and one dimension is 0.35 meters. Terrible 3D artistry here. Yeah. Okay. And we don't know what the length is. And it says, how long would it have to be to suspend a person that is equal to 75 kilograms? So if I did a free body diagram for this person, I'd have their force of gravity pushing down, and then on each foot, there would be a buoyant force. And the idea is that 2 times the buoyant force would have to equal the force gravity. So the force buoyant would be the force gravity, which would be 75. Times 9.8, then you got to divide by 2. So for that I got that this would equal a buoyant force of 367.5 newtons. Now if I set that equal to the actual definition of buoyant force, which is the density of the fluid times gravity times the volume submerged of the object, and in this problem it was given that the density of the water is 1,100 kilograms per meter cubed. So my force buoyant, 367.5 newtons, would equal my density times gravity times the volume, which volume would be base times width times height. So I've got 2 of those variables. And so I can just solve that for the length, and I get that the length would have to be 0.43 meters long. Next, I'm going to look at chapter 15, so problem 49. And in number 49, we're talking about plaque building up in the arteries. And so they've got a cross section of an artery that's constricted in this region, again, due to plaque buildup in the walls. Very common occurrence here. And initially it starts with a diameter of 1.1 centimeters and it constricts to a diameter of 0.75 centimeters. In the first section, the blood flow was 15 centimeters per second, and it reaches the plaque buildup region, and we want to know what is the speed in this section, and then what is the pressure drop between the two regions. So for part A, I'm just going to use the equation of continuity. A1 V1 equals A2 V2. Remember that area is the cross-sectional area, so it's pi r squared. So to get the radius, I have to actually first divide that by 2. So it'd be pi times 0.0055 meters squared times 0.15 meters per second equals pi times 0.00375 meters squared times V2. From that, I'm able to solve for V2 to be 0.323 meters per second. So that's a velocity in the second region. To get the pressure, I can use Bernoulli's law. P1 plus rho G H1 plus 1/2 rho V1 squared has to add up to be a constant, so that equals P2 plus rho G H2 plus 1/2 rho V2 squared. Now the nice thing about this problem is there's no differential in height. Their center lines were along the same line. So we just have to account for the change in velocity and the change in pressure. So if I went to find that pressure differential, P1 minus P2, move that to that side, move this to the other side, it would equal 1/2. I was able to find the density of blood in your text. To be 1,060 kilograms per meter cubed. So it would be this times 0.323 squared minus 1/2 1060 times 0.15 squared. And from that I get a change in pressure of 43.4 pascals.